Well, hello and welcome to this exercise on finding the volume of a complex shape. Now, in this case, the complex shape is in the form of a swimming pool. And we shall also be looking at interpreting graphs. Okay, now it says the diagram shows a swimming pool in the shape of a prism. Now, this is a prism because viewing this swimming pool from this angle, from this elevation, shows that we have a uniform cross section all the way. Sorry, that's supposed to be a straight line, by the way. A uniform cross section all the way from the front to the back. Right, you got to be very careful here because from this elevation, we've not got a uniform cross section. So as long as this object has got a uniform cross section from at least one elevation, then this becomes a prism. Now from this elevation, the cross sectional area at the front here is not the same as the cross sectional area at the back. You see what I mean? So we're looking at this prism from this elevation there. Okay. Right. It says the swimming pool is empty. The swimming pool is filled with water at a constant rate of 50 liters per minute. Work out how long it will take for the swimming pool to be completely full of water. Now give your answer in hours. And then it says 1 meter cubed is equivalent to 1,000 liters. Now, in some situations, you're supposed to know this by heart. So this will not be given to you. So you're supposed to memorize this, that 1 meter cubed is equivalent to 1,000 liters. Okay, now moving on. Now, what I've done is to say, to divide my swimming pool into two sections, sections A and section B. Now, section A is a rectangle and section B is a right angled triangle. So the area of section A will then be 15 times 1, which is 50 meters squared. And the area of section B will be 9 times 1 divided by 2, because we are looking at a right angled triangle. So if we add both areas, the total surface area from the front elevation becomes 15 plus 4.5, which now becomes 19.5 meters squared. Now, to find the volume, we then multiply this cross-sectional area by the depth of the swimming pool, which is now 10. So if we multiply 19.5 by 10, we get 195 meters cubed. And because 1 meter cubed is equivalent to 1,000 liters, so if we multiply 195 by 1,000 liters, by 1,000, we get 195,000 liters. So the volume of the swimming pool is 195,000 liters. Now we want to find how long it will take to fill up this swimming pool. We then divide 195,000 by 50, and because we want the time in hours, we divide it by 60. So it will take 65 hours to fill up this swimming pool. Okay, right, moving on. That's the first part of the question answered. Now, this is the second part of the question, which says, here are 4 graphs A, B, C, and D. Write down the letter of the graph that best shows how the depth of water in the pool above the line Mn changes with time as the pool is filled. So Mn is there. So we're filling the swimming pool above Mn, so to speak. Now, if you look at section A, excuse me, writing section A, sorry, section A and section B. Now, these two sections, the A is in effect a rectangle, while B is while B has got a right angled triangle. Okay, so in effect, when water is introduced into the swimming pool, we expect a change of gradient at some stage. Now, for section B, there is no, sorry, for graph A, there is no such change in the gradient. Graph A seems to indicate that the cross-sectional area is a rectangle. So A is not our answer. Right. Neither can it be D, because there is no discernible change in the gradient of the graph. So it cannot be graph D either. So it's going to be either graph B or graph C. For graph B, you can see that for graph B, there is a change in gradient as time goes on. So it's not graph B. Sorry, it could be either graph B or graph C, because in graph C, there's also a change in the gradient of the graph as time goes on. Right, now I should try and discuss this in more detail in the next slide. Right, now in this slide, again, I've created two, I could create more. I've created two triangular prisms. The first one is in red over here, and the next triangular prism is in purple. So if you look at this at the cross section of these two triangular prisms, it looks something like this one here. Now between time 0 and time 1, the water is filled to this level here. And between time 0 and time 2, on time 2, water is filled to the purple line there. So in effect, if we now look at graphs C and B, because between time 0 and time 1 and between time 0 and time 2, there's an increase in volume. Now, because your water is being introduced into the swimming pool at a constant rate, therefore, the rate at which the depth of water changes will be smaller, or compared to the rate at which changes between time 0 and time 1, because from time 0 to time 1, we've got a smaller volume there. So what we then have is the change in the depth of water between time 1 and time 2 will be similar to this this rectangle here. Okay. Now, if you superimpose that to the change in the depth of water between times 2 and time 3, we have this here. And you can see clearly that the change in the depth of water between times 1 and 2 is greater than the change in the depth of water between times 2 and 3, because the volume has increased and therefore the change in the depth of water will be smaller. So the graph we're looking for will be graph C and not graph B, because the reverse is the case for graph B. Now, I hope all that made some sense, and please subscribe. Thank you for watching, and bye bye now. Bye bye.